Okay, so in this video, we're going to revise how to use the remainder and factor theorems with algebra. So remember, the remainder theorem tells me that if I'm trying to divide a polynomial p of x by some factor x minus a, then the remainder is going to be given by p of a, which means I substitute this value of a into p of x, and whatever that number comes up with, once I simplify that, evaluate that, is the remainder if I was to divide. So it tells me very, very quickly what the remainder is without going through the whole step of long division or equating coefficients to try to find out if I can factorize it. The key part, I guess, is the factor theorem, though. It comes directly out of the remainder theorem. If this remainder happens to end up being 0, then that tells me that the thing I substituted in comes from a factor. So if I substitute it in and I get 0, I know that I have just found a factor of the polynomial. So for these examples here, there are 4 of them, we're going to find the remainder of each one without doing long division and decide if x minus a is a factor. So the first one, you have p of x is this thing and x minus a is this thing. So p of x is that. P of a, now the question is, what value do I substitute in? Well, if you notice, we have x minus a, we talked about before in the rule, and we have x minus 2 now. So hopefully it's fairly clear that a is equal to 2. So I'm going to do p of 2. Now that's going to give me 2 cubed plus 5 lots of 2 squared minus 7 times 2 plus 10. If I do all that, 2 cubed is 8. 2 squared is 4 times 5 is 20. 7 times 2 is 14 plus 10. That all simplifies to 30, 38, 24. So I conclude that x minus 2 is not a factor of p of x because it doesn't come to 0. Let's try the next one. There's my p of x. Let's substitute in 1 because a will be 1 in this case. Again, x minus a and x minus 1 line up. A must be 1. So p of 1 is 2 times 1 cubed minus 5 lots of 1 squared plus 1 plus 1. Doing that, you're going to end up with 2 times 1 cubed is 2 minus 5 plus 1 plus 1. Oh, it's close, but it's not quite. It's negative 1. Therefore, x minus 1 is not a factor of p of x. Next one, we got p of what this time? Well, x plus 3 and x minus a. Hopefully we can see that a must be negative 3 for this to work. If I put negative 3 in here, I get x plus 3. So negative 3 is what I substitute in. So you get negative 3 cubed plus 11 times negative 3 plus 12 lots of negative 3 minus 15. And you can fairly clearly see it's not going to get to 0, but let's finish it off. Negative 3 squared is 9 times 11 is 99 minus 36 minus 15. So the 99 is much too big for everything else. 99 minus 36 is 63. Take away another 27 is 36 actually, minus 15, you're left with 21. Therefore, x plus 3 is not a factor. Of p of x. Gee, I really hope this last one works, otherwise none of them are going to be nice factors. All right, last one, I'm going to substitute negative 1 in. Negative 3, negative 7. Let's doctor it a little bit to make sure it works. Okay, so I think that's going to be fine. So negative 1, let's try that. So 3 times negative 1 cubed minus negative 1 squared plus 7 times negative 1 plus 11. Okay, Negative 1 cubed is negative 1 times 3. Negative 1 squared is 1 times negative 1. 7 times negative 1 is negative 7 plus 11. Oh, look at that. That's 0. That worked out nicely, didn't it? So that means x plus 1 is a factor of p of x. And that is how you use the remainder and factor theorem.